Doc here with Chapter M, Aberrations, Physics 101, Light and Visual Phenomena. Now, an aberration is something we don't like, thus the name. For example, when white light hits a piece of glass, you basically get the color spreading out, like the rainbow effect. This is called dispersion, the fact that the blue light bends more than the red end of the spectrum. Now, this is a law of nature. There's nothing wrong with this. This is perfect display of physics. However, we refer to it as an aberration because we're taking photographs. We do not like it when our colors get spread out in a picture. So here the blue light is focusing right where that point is, closer to the lens. The red light's focusing farther away. For the diverging lens, when the light bends upward, the blue focal length is closer to the diverging lens and the red one is farther away. The effect for blue is more pronounced. You can remember this as blue bends more, or as a German physicist once told me, the E sound in red and less, they basically are the same sound, so he remembered it by red bends less. Red bends less than the blue. That's called dispersion, the fact that the color is spread out, and circles of confusion refer to where there's blurriness. When the blue is sharp, the red is fuzzed out, and when the red is sharp, the blue is fuzzed out. The least circle of confusion is somewhere here between the blue and the red, a compromise. We can use an achromatic doublet to correct for the aberration. Here is an achromatic doublet. A doublet means two lenses. Here you have your converging lens where you see the blue bending more than the red, and a diverging lens with a different type of glass can bring the rays pretty much closer together and help to minimize this effect. Another aberration is called spherical aberration. Now, we like to cut glass as a sphere, grind them out as spheres because it's cheaper. However, when you do that, the rays that are approaching the lens at the margins near the edge, these bend too much when compared to the rays that hit toward the middle. See? And that's a problem also. Now, I am exaggerating these effects in both cases so we can illustrate the idea. Now here, the point that's nice and sharp for the middle rays is way out here. And if you put your screen there, that would be nice. But look at these rays here, which I have color-coded blue. These are going to give you a big smear out there. If you look at where these rays color-coded blue meet, there's a smeared out version of the rays from the middle. See, so the blue ones are the marginal rays, and they come to a focus here, but look at the other rays from the middle. They're not focusing until way out there. So this is the least circle of confusion. This is the least blur, and this is an annoying feature because when you take photographs, you do not want to have these points at different places. Well, let's look at what happens for another aberration, the set called the off-axis aberrations, and these are more problems for photography. There's a blur that occurs for points away from the axis. So here's a point that's away from the axis. This is your optic axis, and this point is off the axis, and you get a point with a little tail, a little flare, like a comma, all right? So that's called coma. Off-axis point is fuzzy. And curvature field, when you have a nice vertical object here, you're going to have a curved image over on the other side. I remember going to a Philadelphia movie theater that had a curved screen to help minimize curvature of field. Then we have astigmatism, and astigmatism here refers to the point from, say, the head. Say I'm standing up here, that's my head, but you're looking at me from the side. That will focus at a certain point behind the lens on the right-hand side. But if you look down from the top, and that's my head, you're looking from the ceiling now, then the rays that fan out this way, they focus at someplace different. This is, again, bad news. You want these points to be the same. That's going to introduce fuzziness. Then we have distortion. If we have an opening here, and these openings are called stops, very important in photography to control your aperture, This grid is supposed to be rotated facing the aperture. I simply drew it this way so you can see the grid and how it gets distorted when it goes through the aperture. And if you put the aperture on the other side, you get this kind of distortion. This top one's called barrel distortion. This is called pincushioning distortion. But the neat thing about this is that you can cancel the effect by having a stop in the middle. That's your aperture control for your camera, and put a lens on either side. Then this effect gets canceled. So a lens can have, camera lens can have 6 components, pieces of glass that act as a single compound lens with a net focal length. And you would have, for example, the achromatic doublet that we mentioned earlier, and 2 systems here of glass components to minimize, to get rid of this effect. And so, $100 lens or expensive lens can have many pieces of glass. All right, let's look at here the dispersion again. And here we have a prism where the light goes through the prism, bending, blue bending more and bending more again as you go through, and you get the colors of the rainbow spread out here. So you have the violet end down at the bottom and the red end at the top. Oh, but now we like this. We think this is cool. So, but we call it an aberration when we're discussing photography. But now we like it for diamond rings. We like the colors spreading out. See, so we are fickle in how we feel toward physics sometimes. Here is a dispersion table for crown glass and diamond. So crown glass, see 1.5. That's what we learned was the index of refraction for glass. Now we're looking at more precisely the difference here. When you look at violet, 1.538, red, 1.52. The violet has a little greater index of refraction, so it bends more. So if you have here 1.54, $1.54, $1.52 or so, like you're basically looking at a penny on a dollar is 1%, and this is close to 1% if you want to round it off among friends. Here for a diamond, index of refraction is 2.4, and now we're seeing more precisely the different colors have different values. If you think of this as $2.46, $2.41, that's roughly 4 or 5 cents. You have 2 cents on the dollar, then you'd have 4 cents on $2, 5 cents. That's about 2%. So you can check this with a calculator that this is roughly the case. The deviation, the variation in the crown glass is about 1%. And the diamonds too. Makes diamond more desirable because the colors spread out more if you want to make a diamond ring. So that's neat. Then we come here to another cool thing, and this is double refraction, where you have certain materials like this calcite crystal, for example, is an example of birefringence. That's what this is referring to. Bartholin here discovering this property, where you have the light, when it comes in, the light, when it travels into the calcite, the velocity of light inside calcite is different depending on if the wave has a polarization, say vertical versus horizontal, or you can orient the calcite so we can look at horizontal and vertical as the 2 main polarizations. The bending of the light, the refraction will be different, and the light will split up. You get a double image. You'll get double image. See, the calcite crystal does not transmit the light equally in all directions. It has a preferential direction. So when the light has the polarization, the electric field is wiggling. The molecules can wiggle and pass the wave better with one polarization versus another. So the light breaks up, and you get then the ordinary ray, ordinary refraction, and what Bartholin called the extraordinary ray. Very, very charming fact, and he loved looking at these things. And this is when polarization was discovered around this time, see, because of this effect. So let's look here at another example. You can check this, of course, do an experiment with the polarizer that Land discovered, and we the cheap one you can get now based on Land's work, the Polaroid, and you can then check these. Here, if you look at this neat effect, if you look at polarized light in vertical and horizontal. Now here's how you have to do this, because this is the 3D making a 2D diagram. Remember that for the electric field, it has to be perpendicular to the direction of motion, the direction of propagation of the wave. So the wave is going this way. That's the way the wave is going. So you can be wiggling up and down, or you can be wiggling in and out. That's what the little dot means. You're wiggling in and out of the page, in and out of the computer monitor. And that's a transverse wave. Don't worry about the magnetic field. Just focus on the electric field. That defines the polarization, as we discussed earlier in our course. So here you have polarization. You can think of that as a vertical, if you tilt your head slightly, and then this dot is sort of a horizontal. Now, when the light hits the glass, you get some refraction and you get some reflection. Now, on the reflection, this is interesting. When this is a 90-degree angle, then you find that this, what we call vertical, if you tilt your head, that would be this way on the reflection. That can't go to your eye because that would be a longitudinal wave. You can't have that. You can only have the sideway motion. So when this thing bounces, this one is going to wiggle like that. It can't do that and go to your eye, but it can go this way. So what happens is that this one going down that way can have both types of wiggles, the polarization, which is the vertical, which your head tilted, or the in and out. But this one here is only the dots. You cannot have the other. So when light hits glass at about a 56-degree angle, the light is polarized. And this is neat because this is like a glare. And if you put a polarizer, you can kill this. You can knock this out, and that can get you a better picture. So that's a little tricky, but just think of the dot as the electric field moving into the monitor and out of the monitor, and the line is the direction of the oscillation for the other polarization state. That's neat. And here we have liquid crystal display, fascinating stuff, where you have a material where these liquid crystals, look at them as like baby French fries here, where what they do is they rotate the polarization state. So if you have a polarizer here to make this light polarized in a vertical direction, this twisted cell will make that polarization rotate so that it's no longer vertical, but it is horizontal. Then if this polarizer here is rotated so that it lets the horizontal through, then you get a bright light. Now, the neat thing about these crystals, if you zap them with an electric field, and they all line up, then there's no rotation, and this would pass straight through, but now this is crisscross compared to that one. And remember in class when we did the crisscross with polarizers, you get nothing. It gets dark. So that is really neat. And you can then make a little watch with the little liquid crystals to make little numbers, and by controlling the little currents, you can have little dark regions and make the like 4 or 5, a calculator, and those really use very little electricity, and you can have a battery that can last you for years. So that's a liquid crystal display. Very, very nice principle. So just think of these having 3 properties: a mechanical property that if you twist them, they can be twisted like this. If you have a group of them and twist the 2 walls on either side, you can twist them. That's a mechanical property. They have an optical property in that they rotate the polarization of light 90 degrees here when you set it up like this. And they also have an electric property where if you zap them with a little electrical field, you apply electric field, they line up. And when they line up, you basically lose the twisting effect, and the light just passes straight through. So you can get dark and bright regions on a display, the liquid crystal display. Polage is the last thing we will look at. And for the polage, I will show you a nice picture of one. And here we go. There's the artist, Austin Wood Camero, who invented the art form, polage, polarization, sort of like a collage. And this is really neat. She uses no color. In other words, when I say color, I mean no paints or no colored pencils. The color is coming from the polarization, and the property that some materials will have, give you different effects for different wavelengths. The color, for example, different colors will undergo different effects when they go through the birefringent material. And by very cleverly controlling these, she can make something that has color, and then if there's a polarizer that rotates, say in front of this, you basically get the complementary colors when it rotates 90 degrees. I'll let the artist explain in her own words how this works. I began developing polarized light collage, in 1967. It consists of layers of clear cellulose sandwiched between two polarizing filters. See, that's the secret to polarizers. Polarizing filter is used in Polaroid sunglasses, polarizing filters for camera lenses, and the liquid crystal displays. Very few people are aware of the phenomena which occurs when certain birefringent materials such as cellulose, mica, stressed plastics, and sugar solutions are viewed between two polarizing filters. White light, as it passes through, becomes separated by wavelength, color. I am able to control the color by collages by the thickness and orientation of the tiny little pieces of cellulose which makes up the image. Amazing how she puts that together in an artistic way. Very, very cool effect. So the two secrets here, one, the polarizers, and also the birefringent material, the materials that she used that gets the nice, beautiful effect.